This is the 8th video in the Beginning Artificial Intelligence series. In this video, we are going to look at how to load and save datasets in neural networks, and then we're going to look at an example which uses image manipulation, analytics, Keras, TensorFlow, and what we're about to cover to make a neural network that can classify 101 objects plus background images. To begin, we're going to look at load directory dataset. Load directory dataset takes a path and two functions, which could be lambdas, which will load the X data from a file and load the Y data from a file. This function can handle two directories. It can have a directory that looks like this, which is the top one here, and it will split the X data and the Y data to different folders, and this will be all the X data, and this will be all the Y data. This is useful if you wanted to have an image, a bunch of images here, and make those images become audios here. So you could hold the audios here and the images in this one, and then you could train it. And of course you can see we have tests data here, train data here, and validation data here. You don't need all of them. You especially need train data though, but you don't need the others. We also have another one. Another directory looks like this, which is the bottom directory shown in the comments there, which we just make a train data, and then this is X data, this is X data. This is the name of the Y, so this is for classification. So it will make a one-hot encoding of these names. So this would be 1, 0, this would be 0, 1. So this is useful for classification. You have to pass, well, when you create it, you don't have to, but so you can see how this is. But if we go to save real quick, you can see you have to pass a label. So this function will actually create this whole thing, and you have to give it labels. So this could actually be called, if we go to this example over here, it could be called airplanes. You have all your images, and it's going to classify these as airplanes, but it's actually going to be a one-hot encoding. So it won't actually be called airplanes. It'll be a one-hot encoding, which you can obtain when you load it. Okay, so that's kind of how that function works, and this function pretty much works the same way. You give it a dictionary, and it will save it. So the other just loads it. This one will save it. The one thing you have to watch out for is when you give it a path. Say we have the path called saves. If we don't have that, if we haven't created a path called saves, it's not gonna make it. You have to give it a path that exists, and then it's gonna make a train X, train Y data folders, and then the data files and the other data files. Okay, and now we also have this function, these two functions right here. This will load from a single file. You can see right here we have data.h5, and it will load it from there, and it will return a dictionary, or we can save it to one file from a dictionary. And this is just code testing it. If you wanted to run it, you could. All the stuff will be on my GitHub. Okay, so now we're going to look at neural network real quick. This has two classes, which are split into trainer and predictor. The reason why I split them up like this is because for certain projects, you don't actually need it. So let's say an example would be like face recognition. You have your data set, you train it. You don't actually need the predictor because you're training it, and it will evaluate when you're done calling it. But the predictor is useful if you want to just show it off. So if you made an app or something and you just need to predict, you don't need to train anymore. You're just predicting, so you can just use this, and it's a lot less code and it's a little more simplified. So that's why I split it up into two functions. It's especially helpful just logically of what you're doing. Instead of just having one model, you never know necessarily, are you training the model, or are you just predicting the model? So this makes it more explicit. Alright, so you can see this takes two parameters right here. You don't need them if you give it a dictionary. So data can be a dictionary or a string that's a path to a directory or a file. If it's a path to a file, it's going to assume it's a .h5 and it's going to load it like that. Or if it's a folder, it's going to load it like this, or it's going to load it like this. And if it's a dictionary, it will just load it like, as long as you have the train X or train X like this, or train X like, or test X like that, validation X, or train X like that. As long as you have that, make sure you have your train X and train Y data, or it won't work. It will throw an exception, as you see right here. Okay, so now when we have the train function right here, when we're training, you give it the epochs. You don't have to give it data. We already have the data from when you initialized it. You can give it batch size, the callbacks, and verbose. Pretty much just uses this function, which is part of Keras models, and to train. And then we just, if it's verbose, which is true or false, we'll print out an evaluation of the test data. And if we have validation data, it will print out that. If we have test data, it will print out that too. Now, if we wanted to save this once we're done training it for, let's say, an hour, we can save it after that, and it will save it into a directory we could call, again, saves or something, and it will create a new folder with the time of when it's saving it that contains the weights and the model architecture and notes, which these notes, if none, will just be a model summary, which I'll show when we get into the image classification over here. Now we have our predictor. Oh, wait, skip the load right here. So load is pretty much, we'll just load from a save. You have to give it an optimizer, loss, and metrics again, though, because it doesn't say that when you do the save function. And now a predictor literally is just this code here again. So it's just in the initializer this time. And you could pass weight names and model names. Let's say you could have changed it, so that's kind of why I have this here. But it will load that all. It will load the architecture and the weights. And now you can predict. This function predicts everything. If you give it like multiple x values, it will predict. This one just handles one x value. Now I have a couple functions down here that just make it a little easier when you're making a Keras model. This dense function right here will return a function that creates, well, that will return a tensor, which is the same as all those previous examples in my earlier videos of how to make a Keras model. This can just be changed with that. And what this does is it will just make it so easy to have a batch normalization layer. You don't have to type all this out. You just say true or false if you want it. If you say true, it will disable the biases, because you don't need biases if you use batch normalization. So it does all the logic and simple stuff. It does some stuff for you to make it a little simpler. We also have our convolution 1D here, which is going to add a couple extra things so that you don't have to type them. If you want batch normalization, you can have true. But you can also do max polling or upsampling. Max polling is pretty much a downsample that takes the highest value out of the pool size, and it just gives that one value. So if we had 3, it would take 3 values and it would only output 1 value. Upsample is the opposite. It can take 1 value, it could output 2 values. So you could just enable that stuff by giving it a size, and if you wanted the strides too. Convolution 2D has everything Convolution 1D has, but it also can transpose, which is an extra thing, which pretty much is a deconvolution layer, which will actually have the potential to enlarge an input. So instead of like the upsampled one will actually enlarge the output, but this time it's just a single convolution layer, which Keras has right here if you wanted to use it without this function here. And now we also have an inception function, which just helps you create an inception network. You can look that stuff up if you wanted to go into that. And then we just test the code here. Now let's actually get into image classification. The first thing you need to do is you need to download the dataset. First, you can go on this website right here. This is from Caltech. You can download it right here. Once downloaded, abstract it all. You'll have this folder right here. You're going to have all this data in here. You're going to want to drag all this data into a folder you can create called train data. And then once that's done, you're going to want to go to background Google, and there's going to be a file called TMP, and you're going to want to remove it. And then you're all good for the dataset. And then you're also going to, let me just remove this real quick. You can test it. If you don't download the dataset, so if you don't download this from the GitHub, or if you remove it, we can actually recreate it here. But first, let's just look at how we import some stuff real quick. So I import 4 modules from the utils package, which isn't released, so we just have individual modules, so it's not packaged quite yet. And you can, if you have a GPU, you can enable allow growth, which you'll have to enable like this. You don't need to enable this if you have a GPU, but I like to allow growth because it won't allocate the entire GPU's RAM. It will just use what it needs. And now you can enable training. If you want to train, put that to true. If you already have trained weights that you would like to load before you train, or for prediction, you would want to give it there. And then now we can go look at how we can create data. So right here, or the data set. Right here, it checks that you actually have the data set that I just showed you how to download. Then it checks if you have that file, if this file exists. Now I have it too, so it's going to say it doesn't exist because I added that to there. And we're going to create the data set after we load from the folders here. So it's going to load this. We're going to do some stuff, and we're going to get one file. And what we first do is we make an analyzer. We look at the distribution of the labels, and we can actually run it real quick on. We can look right here. if we run it, it's going to take a little while, but so I'll just have it off to the side. But we can look at the distribution in a second. While that's going, we can look also, we make, this is the windows from the image path. We made it right here. And we just add 3 windows to view the data we're making. We then have a data multiplier, which up at the top was set to 5. And what that does, we're going to mutate the normal data. So the images we just downloaded, we're actually going to mutate them. We're going to change the gamma. We're going to rotate it. We're going to translate it. And we're going to save that back to the trained data set. But we also have another one down here, which is going to be used for the test data set to make sure we're not overfitting. Okay, so it's done loading now. And you can see the distribution is kind of weird. We have almost 500 for the background images, but we only have like for the lobsters 41 or inline skates 31, but we also have like almost 800 for motorbikes. So you can see it. It's not like equally distributed. So that's probably going to be a little problem. I'm not going to adjust them or anything because I don't want to lose the information. Now the Google one's actually fine, I would think, because they're all different images. So that's kind of like background. So it's you don't get from a couple of images what a background is. You have to look at a bunch. But these face ones and these motorbikes, I think, are a little extreme for those values. But I'm not going to adjust them. All right. So now when I click enter here, it's going to, because I don't have a data.h5 that exists in the directory, it's going to create one. And we can look right now. It's going to make those 3 windows. And we can see these are the mutated ones. These are the original. And it's just going to go over all those. That's going to take a little bit, so I'm going to just go off from there. And we can see right here, when we do make the whole data set, we save it, or we make it a NumPy array if it's not one. And if this is for color. So if you're not using color, we do this instead. This will just expand the dim so we can use the convolution layer on it. All right, and now I had this set for a little bit. This can improve the accuracy, but it will make everything afloat when you save it, so that's going to be larger. So you don't necessarily want to do it. I for the trained weights I'm going to give you on my GitHub, it's not, they weren't trained for this, so don't have that commented if you're going to use my trained weights. Okay, and you can see we use that save function right here, and we save the data set and all that. Okay, so now we get into training. If this is true, we're going to do all this stuff here. So the first thing is we make sure, are we using color or not color? If we're using color, there's going to be 3 color channels. If not, we're just going to have that 1 grayscale value, and we pass it in here, and then we make the model. Now this is a pretty big model. It has more than it has 26 million neurons, so that's pretty extreme. We could cut all these values in half, and we'd probably be okay. But I wanted to make it better, or you could do this right here, and you could cut off right here. But of course, my weights that I'm going to have on GitHub will not be trained for that, so they'll be trained for this. Okay, and now you can see we're using all these functions from the neural network module here, these functions up here that I just went over. So when I'm actually doing the output here, default is batch normalization, but we don't want batch normalization for the output, so we set false for that. And then we compile the model and make it. We print out the summary, which we can actually see. I have right here. This is what a summary looks like. It just tells you the architecture of the model pretty much. And we load it. If we give it a path, we'll load the weights before we train. We get the time so we can actually print out how long it actually took the whole thing. We use the epochs, which at the top are 25, and the batch size is 64. Now normally I go with a high batch size, but because I didn't want to overfit the data and we're using batch normalization, I'm setting it to a lower value, so it will take a little longer. And then you can see once it's done training, we're done all this, and now we make the predictor. So if we were actually doing a real project, we'd probably split this into a different file, Python file, and this into a different Python file, and even the data creation could be in a different file too. Now for the predictor, we make an image, a window for the image, and we load the data. This is just to test it. So in a real world example for face recognition, we wouldn't be using this. We would probably be using a camera, which gives us live feedback, live information. But just for testing, we're not doing that, so we just have this. And we go over the whole data set, and we squeeze the information now because we're trying to make a window. So you, at the very top of here, when we made the data set, we're down there I'm assuming that it's gray. I should probably add some logic not to assume that, because it could be color. But if it's gray, then you can see why we would squeeze it. Now if it's not, when we call squeeze, it can't squeeze it, so it's fine. So that code down there is fine, I think. But if it's gray, it will squeeze it and it will make it so the windows work. And then we predict it, and we just print out the prediction, which we can see right here. So for this one background image, which we can view right here, it said it's a background image with 45% confidence, and the true class was a background image, so we were correct. If we click next, we can see this time for this image, it totally thinks it's the background image 100%. Of course, I am rounding the values right here, so then it's probably not exactly 100%, but it's close enough. Okay, so that's pretty much all this stuff here. And in the next video, we're going to get a little off topic, and we're going to look at genetic algorithms. And after that video, we'll probably get the genetic algorithms back on topic by using them to train hyperparameters for our models. As you can see here, these values can be a little annoying. So like, how do you know like 64 or 3 or 2? And this is, I didn't ever explain this. This is the kernel size, and these are strides, and this is the filters. So how do you know we should do 3? How do you know we should have 2 here? How do you know there should be 64 and there should be 2000 almost? So we can use some hyperparameter tuning, and a future video will probably show that. Okay, see you in the next.